Good afternoon, everyone. I'm Feng from Los Alamos National Laboratory. Today, I'm going to talk to you about experimental measurements of ion diffusion coefficients and heating in a multi-ion species plasma shock. Before I start, I want to give you a brief introduction to our facility, Plasma Liner Experiment, PLX at Llano. PLX is a multi-million-dollar project supported by APE Alpha and Beta program. It is built to investigate a reactor-friendly alternative approach to fusion energy named magneto-inertial fusion or magnetized target fusion, which is a hybrid concept of magnetic and inertial confinement. So in this concept, a magnetized plasma target is injected into the chamber first, and then it's heated, compressed and heated by a heavy, fast-moving plasma liner formed by plasma jets generated by these plasma guns. So currently, we have 36 plasma guns installed on PLX. A quick shout out to our poster presentations tomorrow morning if you wish to learn more about PLX and our research. In this talk, the multi-ion species plasma shocks are generated in this small cylindrical chamber by head-on colliding two plasma jets, which are generated by these two plasma guns borrowed from PLX. So here's the outline. To begin with, I'll explain to you why we're interested in studying multi-ion species plasma shocks. Second, I'll briefly show you the theory on inner ion species diffusion, which occurs in multi-ion species plasma shocks. And then I'll move on to the main part of my presentation today, which is about experimental measurements of ion diffusion coefficients and 1D simulation that we use to compare with our experimental results. And finally, I'll summarize my talk. The first question you probably would wondering, what is a shock wave? A shock wave is a propagating disturbance that moves faster than the local speed of sound in a medium. Here's a good example of the shock waves seen coming off a supersonic jet using Schlieren photography. Shock waves are also commonly found in space. So solar wind travels supersonically at a speed of 400 kilometers per second. So when it encounters a planet, it slows down from supersonic to subsonic, creating a bow shock near the planet. Since a plasma is also a type of fluid, you would expect similar shock features existing in a plasma. So plasma shocks are an important feature in astrophysical systems and high energy density experiments. In fact, the bow shock example I just showed you earlier is also a type of plasma shock. Plasma shocks are governed primarily by Coulomb interactions between charged particles or the influence of the electromagnetic fields in the shock. In addition, if a plasma is composed of multiple ion species, the plasma shock would contain more features, such as inner ion species diffusion. The interest of studying this type of diffusion initially arises from inertial confinement fusion experiment. So here's a sketch of a fusion fuel pellet used in ICF experiments. it usually contains a 1-to-1 mix of deuterium and tritium. Both are heavy isotopes of hydrogen. ICF systems generally use either laser beams or X-rays, the driver, to illuminate the surface of the target. And then the heat applied by the driver will cause the outer layer of the target to explode, generating a shock wave. And then the shock wave will compress on the fusion field until it reaches thermonuclear burn conditions. In ICF, the inner ion species diffusion between deuterium and tritium ions occurs during the shock transit phase. Understanding the evolution of this plasma during this phase is fundamentally important for understanding ICF ignition, because it sets the initial conditions for the hotspot formation, compression, and burn. In recent years, inner ion species diffusion theory has also been adopted in magnetized liner inertial fusion, MagLIF, to study energy and magnetic flux losses. So you have seen so far, the inner ion species diffusion plays an important role in both ICF and MagLIF. However, our understanding of this type of diffusion is still relatively new. In fact, it's only within the last decade that we have ever considered inter-ion species diffusion in ICF. In addition, this underlying ion diffusion model used in previous simulation and theoretical works has never been directly validated by experiment before. Therefore, we're highly motivated to study this type of diffusion in multi-ion species plasma shocks. Before I jump to the experiment, I want to briefly show you the theory on inner ion species diffusion. So here's an overall big picture. Theory and simulations predict that the lighter ion species will diffuse faster than the heavier ion species within the collisional plasma shock. To understand why this is the case, let's first look at the simple diffusion model. So if you dissolve some particles in a glass of water, these particles will tend to stay in one place at first, but then they will start to move around in the water due to the concentration gradient. Of course, in a plasma shock, things will get much more complicated. The ion mass flux is not only driven by the concentration gradient, but also by some other thermodynamic forces in a plasma shock. For example, the gradient of the ion pressure, gradient of the ion temperature, gradient of the electron temperature, and finally, the electric field across the shock. So these are the mathematical expressions of these diffusion coefficients in the previous equation. I'm not gonna get into too much details, but if you are interested to know how these coefficients are derived, you can refer to the details in these references below. Okay, so here's the plot showing the profile of the ion temperature, electron temperature, potential, and density across the plasma shock. So the left side is a post-shock region and the right side is pre-shock region. Due to the gradients of these quantities, the ions inside the plasma shock will start to diffuse towards the pre-shock region. So the ion diffusion model I mentioned earlier predicts that the lighter ion species will diffuse faster than the heavier ion species, causing the two species to separate inside the plasma shock. So to experimentally validate this ion diffusion model and observe species separation, we create multi-ion species plasma shocks by head-on colliding two plasma jets in this cylindrical vacuum chamber of about 130 centimeters in length and 70 centimeters in diameter. The plasma jets are created by these two plasma guns installed on the opposite side of this chamber. So at the time when the plasma guns are fired, a gas puff consisting of 50% argon and 50% nitrogen is first pre-ionized in the gun nozzle and then accelerated into the center of the chamber by J cross B force at a speed of 18 kilometers per second. We also have a suite of diagnostics available to measure the plasma parameters and image the shock formation. For example, we have photodiode arrays here placed at each gun nozzle to measure the jet speed using time of flight analysis. This is a 5-chord heterodyne interferometer, and we use that to measure the electron density in the plasma shock. A high-resolution Doppler spectrometer is utilized to measure the ion temperature by examining the width of the Doppler-broadened ion emission line. Here is a survey spectrometer. It records the broadband ion emission spectrum, which is later compared to atomic modeling to determine the electron temperature in a plasma shock. Last but not least, we also have a fast intensified CCD camera to image the shock formation. So these are the parameters of the plasma jet in the experiment. The average charge number is close to 1, and the Mach number of the argon and nitrogen ions is about 8.2 and 4.9 respectively, suggesting that the both species in a plasma jet are supersonic before the head-on collision in the center. The ion temperature and the electron temperature are similar, close to 2 eV, and the density of the shock is density of the jet is about 5 times 10 to the 14 per cubic centimeter. So these are the images showing the time evolution of the jet merging recorded by the ICCD camera. So the time here is referenced to the moment when the capacitor banks discharge. As you can see here, at 50 microseconds, the two jets are seen to reach the center of the chamber and about to collide. And our sharp shock feature appears only in just like 7 microseconds. This is an example of a broadband ion emission spectrum recorded by the survey spectrometer. By comparing this to atomic modeling, we found that the electron temperature in the plasma shock is about 2.2 eV. So here's an example of the Doppler broadened ion emission line from the high resolution spectrometer. So the ion temperature can be determined by performing deconvolution of instrumental broadening with the measured spectral profile. So this procedure shows that the argon ion temperature in the plasma shock is close to 17 eV. As I've shown before, the theory predicts that the lighter ion species diffuses faster than heavier ion species. This suggests that the density of the lighter ion species in the plasma shock will decrease faster than that of the heavier ion species. So this gives us a way to validate the theory in the experiment. So here are some experimental results. So this is a normalized density of argon and nitrogen as a function of time, where the pre-shock region and the post-shock region is separated by this blue dashed line. As you can see, the density of both ion species increases at the same rate at the beginning. However, after at a later time, after the shock forms, the lighter ion species, in our case, nitrogen, decreases faster than the density of the heavier ion species, in our case, argon. So this is exactly what's predicted by the inter-ion species diffusion theory. We can also calculate the drift velocities of each ion species by looking at the density decay rate here. By doing so, we found that the relative drift velocities between argon and nitrogen is about 460 meters per second. By eliminating the small terms in this ion mass flux, we're able to experimentally constrain some of the leading diffusion terms. As you can see in this table, the experimental values are consistent with the theoretical predictions within errors. So this plot shows the time evolution of the temperature of argon and nitrogen ions predicted from the Doppler spectroscopy. Substantial ion heating and temperature separation is observed during the shock formation, with the temperature elevated from 2 eV in the pre-shock to about 17 eV for the argon and 9 eV for the nitrogen. We have also performed 1D Eulerian ion Fokker-Planck simulation to compare with our experimental results. So the movie I'm going to play to you right now is the time evolution of the ion density in the plasma shock. So the horizontal axis here represents the space between the two plasma guns. So this is the time evolution of the ion drift velocity in a plasma shock. So initially, these two plasma jets are coming towards each other at a speed of 20 kilometers per second. So let's just pause the video a little bit. So you can see at the beginning, so these two species are now separated. However, at later time, after the shock forms, maybe here, yeah, clearly the lighter ion species diffuses further ahead than the heavier ion species. So here's a comparison between the simulation and the experimental data. The first column here shows the time evolution of the density in the plasma shock. And the second column shows the time evolution of the temperature in the plasma shock. So the simulation is in general is consistent with the experimental data, successfully predicting a faster density decay of nitrogen and ion heating and temperature separation. In addition, the relative drift velocity between the two ion species predicted by the simulation is also consistent with the experimental value. However, one of the noticeable discrepancies between the simulation and the experiment is that the simulation predicts a much higher temperature jump compared to the experiment. So the leading edge ions with higher velocity will reach the center of the chamber first and are heated to a much higher temperature. This effect is easily to be seen in the in the simulation. However, it's hard to be observed in the experiment due to the low density of this ion group. So these results are recently published in PRL. So if you want to know more details, you can refer to our paper over here. To summarize, we have presented direct measurements of inner ion species diffusion in multi-ion species plasma shock produced by head-on colliding two plasma jets. We demonstrate for the first time that the dominant diffusion coefficients calculated from the inter-ion species diffusion theory are in general agreement with our experiment. We have also performed a 1D ion Fokker-Planck simulation, and the results show an agreement with the experiment. So this is the end of my talk, and I'm ready to take any questions.
Let's thank you. Yeah. And it's time for question.
So I haven't thought about, well, first of all, thanks for a great talk. But I would think when your plasma jets initially collide, is it two shocks that you generate propagating back to cause the stagnation?
Oh yeah, that's a good question. So in this process, the pre-shock region actually becomes the post-shock, after the shock forms. So they kind of, after shock forms, they propagate to both sides.
So then do both sides experience the same shock strength?
Yes.
And does that have an impact?
Yeah, I think so. It should be symmetric. So.
Okay, because the sound speed in the downstream media could be different, right?
Right, yeah.
So couldn't the shock strengths be different on either side?
Well, so, the shocks kind of like meet towards the center, right? So
you just look at a very brief time in that center period.
Yeah.
Okay.
Yep.
Gotcha. Thank you.
Very nice measurements, Feng. I have two questions. The first one is when you use Doppler spectroscopy to measure the ion temperature post-shock, is it important to attempt to model what the flow velocity of each ion species is in order to properly interpret the Doppler spectra?
Which one you're saying?
So the Doppler spectra just, it's sensitive to the velocities of ions. So it's not just their thermal motions, but also any bulk motion.
Right.
So is the bulk motion fast enough that it affects your interpretation of Doppler spectra?
Oh, I see. So I think the bulk motion will just only shift, let's see. So just a second. So let me see if I can find it. Yeah, so over here. So the bulk motion will basically shift the peak from, one place to the other, but it won't change the width of the line, because that's basically caused by the velocity distribution of the ions.
Okay.
Yep.
And then the second question is, so one of the discrepancies I saw in the simulations versus the experiments is that it actually looked like this in the simulations, the decay rate of the density of each species basically looked the same. It's just one was offset from the other. Whereas in the experiments, it looked like they were locked in place and you actually had distinctive decay rates, right? So to me, the simulation just looks like the same curve and one is shifted over.
Well, maybe it looks like that, but because it's the well, the time scale is like same for both species, so maybe it appears like that way. But because if you look at at some certain time, this density of the heavier ion species, lighter ion species still like decays faster than the heavier ion species. So,
okay, thanks.
Yep, thanks.
Another question? So I have. You are applying magnetic field to just like to accelerate these species, right?
Magnetic field?
Are you applying external magnetic?
No,
field?
we don't. It's unmagnetized plasma.
Okay, when you are talking about this temperature measurement, are you measuring this temperature like behind the socks and like front of socks? Have you measured that? Or is just like an overall temperature?
It's a temperature actually. Because it's a temperature right at the center of the chamber, not like average temperature everywhere. So
okay,
yeah,
but yeah, definitely it's going to be different behind these socks.
right.
Yeah. Okay.
Yep.
Yeah, definitely. And let's thanks the speaker again.